Ashford dilution law or Ostwald dilution theory. According to Arrhenius theory of dissociation, an electrolyte dissociates into water solution. These ions are in the state of equilibrium with the undissociated molecules. So this is called a ionic equilibrium. The ionic equilibrium is established in between the ions, and undissociated molecules. So that is according to Arrhenius. Now here, the Ostwald noted that the law of mass action can be applied to the ionic equilibrium, as in the case of the chemical equilibrium. He tried to apply the law of mass action to this ionic equilibrium. Or it also tells us the variation, see this one, the variation of degree of dissociation of an electrolyte with dilution. So let's see. Now here, considering an aqueous solution of a weak electrolyte, that is AB, see this one. The AB gives rise to A plus B minus. A plus B minus. So this is a weak electrolyte. Initially, what is the concentration of the AB? The initial concentration of the AB is, let it be C. Initially, there is a no product, so that is why there is a no concentration of the products. So that we are writing 0. Now here at equilibrium, then what happens? At the equilibrium, the concentration of the products, the product here it is the A, it is the C alpha, and B is also C into alpha. Then what happened to the concentration of AB? So that is become C into 1 minus alpha. Now here, alpha means the degree of dissociation. Now here, what happened? The Ostwald, he applied the law of mass action to this equilibrium equation. Now at equilibrium, then what happened according to law of mass action? The K is equal to concentration of the products by concentration of the reactants. Then substitute the concentration values of the products and the reactants. Then we can get the this type of equation here. Kc is equal to, what is the concentration of the A plus and B minus? So that is, we know that C here. The concentration of the A plus, it is C alpha, and B minus, that is also C alpha. And what is the concentration of the AB? That is C into 1 minus alpha. So substitute all the values, then we can get this type of equation. Okay. Here what happened? C alpha into C alpha, that is C square alpha square by C into 1 minus alpha. Here 1C, here also 1C cancel. Then remaining, what happened? K is equal to C alpha square by 1 minus alpha. Here, see this. So this mathematical expression representing the variation of the degree of dissociation with the dilution. This gives the information about what? The variation of the degree of dissociation with the dilution. This is known as Ostwald dilution law. This is known as Ostwald dilution law. Now here, for example, for a weak electrolyte, then what happened to the alpha? Yes, we know that the degree of dissociation for the weak electrolyte, so that is very, very small. Hence, what happened here? The 1 minus alpha value, it is nearly equal to 1. It's nearly equal to 1. Then substitute the value 1 in the place of 1 minus alpha in the equation. Then we can get this type of equation. See this one, the K is equal to C alpha square. So finally, write down the equation for the degree of dissociation, that is alpha, then we can get this type of equation. So that is alpha is equal to under root AA by C. Here, so let's see limitations of Ostwald dilution law. So what are the limitations? So here the limitations. So what are the limitations of the Ostwald dilution law? So let's see. The first one, that is the law holds good only for the weak electrolytes. That means this Ostwald law, it is only applicable for the weak electrolytes. It fails completely when applied to the strong electrolytes. In the case of strong electrolytes, then what happens? It fails. And the next one, the value of alpha. See, the value of alpha, it is determined by the conductivity measurements. Conductivity measurements by applying the formula gamma by, sorry, it is lambda by lambda infinity. By using this formula, then only we can calculate the what is the alpha. So that is also one the drawback of the Ostwald dilution law. So these are the some limitations. మరి ఆస్ట్వాల్డ్ విలీన సిద్ధాంతం యొక్క అవధులు మరి ఏమున్నాయి? అవధులు చూసినట్లయితే, సో ఒకటి, ఈ ఆస్ట్వాల్డ్ విలీన సిద్ధాంతం అనేది కేవలం వీక్ ఎలక్ట్రోలైట్స్, బలహీనమైనటువంటి విద్యుత్ విశ్లేషకాలకు మాత్రమే ఇది వర్తిస్తుంది. ఎప్పుడైతే బలమైనటువంటి విద్యుత్ విశ్లేషకాలకు ఈ సిద్ధాంతం అనేది వర్తించదు. సో దాని గురించి ఎక్స్ప్లెయిన్ చేయలేకపోయింది ఈ ఆస్ట్వాల్డ్ సిద్ధాంతం అనేది. అదేవిధంగా ఈ విఘటన తీవ్రత అనేది ఆల్ఫా అనేది కేవలం మనము ఈ కండక్టివిటీ మెజర్మెంట్స్, వాహక విలువలను ఉపయోగించి మాత్రమే ఇక్కడ కనుగొనడానికి అవకాశం ఉంటుంది. కాబట్టి అది కూడా ఒక డ్రాబ్యాక్ గా మనం చెప్పవచ్చు. సో ఇది ఆస్ట్వాల్డ్ సిద్ధాంతము మరియు వాటికి సంబంధించినటువంటి అవధులు. సో దిస్ ఇస్ అబౌట్ Ostwald dilution theory and its limitations. Next one, Debye-Huckel theory. Let's see what is Debye-Huckel theory. So here, in the previous two theories, so that are Arrhenius theory and Ostwald dilution theory, these two theories are only applicable for the or these two theories will give only information about the weak electrolytes. Okay, these two theories are failed to explain the what is the behavior of strong electrolytes. Now here, Debye-Huckel theory here to explain the behavior of strong electrolytes. Debye and Huckel put forward a theory. So this theory is known as Debye-Huckel theory, or also it is known as Debye-Huckel theory of strong electrolytes. So according to Debye-Huckel theory, every strong electrolyte, since we know that every strong electrolyte, it is completely ionized. It is completely ionized at all portions. And also the increasing in conductancy. So according to Debye-Huckel theory, see this one, the increasing in conductancy and dilution, it is not due to the increasing in number of ions, but due to increasing in the mobility of the ions. The electrical attractions, see this one, then explain the electrical attractions among the oppositely charged ions, which affects it. So due to presence of that attraction forces in between the ions, in between the two opposite charged ions, so due to presence of that attraction forces, so that definitely affects the speed of an ion in the electric field. then that is known as interionic effects. Interionic effects. So these are the some postulates which are present in the debatical theory. Now here there are two such effects are present. So that are known as, the first one is relaxation effect, or it is known as asymmetric effect. The second one is electrophoretic effect. The second one is electrophoretic effect. The first one, so that is relaxation effects, or it is known as asymmetric effect. So what is this relaxation effect or asymmetric effect? So let's see. So first of all, in the solution of a strong electrolyte, so because of the interactions, the interionic forces of attractions, each ion is surrounded by an atmosphere of also oppositely charged ions. So for example, see this one, see that this diagram, a positively, see this one, this is a positively, a positively charged ion is surrounded by several negatively charged ions. Three-dimensional. See this one. This is a three-dimensionally. So these ionic sphere are symmetrical. So this arrangement, it is in symmetrical ionic atmosphere. This is the arrangement is a symmetrical arrangement. When you pause the current, through the solution, then what happens? The ions move towards the oppositely charged electrodes. Opposite charged electrodes. See this, for example. So that's the central ion. See this one. The central ion moves in one direction, and the surrounded. See this one. The surrounded anions moves in the opposite directions. So in that case, then what happened? The symmetrical ionic sphere. This one. The symmetrical ionic atmosphere transferred into a asymmetric one. So what happened? There is some disturbance. It is takes place while you pass the current through the solution. Initially, there is a symmetrical arrangement is possible. So after the passing the current, then what happened? Unsymmetrical arrangement is established after passing the current through the solution. So due to this, the positive ion experience much force. See this one. The positive ion experiences a much force of attractions from the behind, which is called the retard forces. So this is known as retard forces. So while moving the cation, see this one, these directions, so all the ions are attracted. Since the ion, the central ion, it is attracted by this ionic atmosphere. Massive attraction forces is present on the central cation. So due to the here, this is known as the retarding force. So thus the mobility of the ion are retarded, and this effect is called asymmetric effect. So this effect is known as, this phenomenon is known as asymmetric effect, or it is known as relaxation time effect. Relaxation time. So next one, second one, so that is electrophoretic effects. So what is the electrophoretic effect? So here, so the solvent molecules, see this one, these are the solvent molecules. So this is the ionic atmosphere, and this is the central ion. So the solvent molecules associate with the ionic atmosphere. This, see this one, these are the solvent molecules which are present along the ionic atmosphere. So due to presence of the solvent molecules along the ionic atmosphere, it causes the retarding system. It causes the retarding influence on the momentum of the movement on the ions. So this phenomenon is known as electrophoretic effects. So these two effects, so that are asymmetric effect and electrophoretic effect, so causes some low conductivity at a high concentration. Here what happened? The movement of the ions, the speed of the ions becomes very slow. So due to presence of these two effects, Then what happened there? Automatically there is a decreasing in the current. There is a decreasing in the conductivity. So that means with the dilution, these two effects are reduced. With the dilution, then what happened? With the dilution, these two effects are reduced. These two effects are reduced and they are minimum at infinity dilution. And the conductivity slowly increases even in case of a strong electrolytes. So here initially what happened? So due to presence of these two forces, asymmetric effect and electrostatic effect. So due to presence of this one, there is a decreasing in the conductivity possible. But when you then dilute the solution, then what happens? These these two effects, electrostatic effect and asymmetric effects are become less, then automatically there is a increasing in the conductivity of a strong electrolytes. So this is about de Broglie theory. So next one, that is de Broglie-Ansager equation. So de Broglie-Ansager equation. So what is the de Broglie-Ansager equation? So let's see. So de Broglie derived a mathematical expression for the variation of equivalent conductance with concentration. So this equation was further improved by the Ansager, and thus it is known as the de Broglie-Ansager equation. So what is the de Broglie-Ansager equation? So de Broglie. So firstly, the de Broglie, these two scientists are derived a mathematical expression for the variation of equivalent conductance with the concentration, and furtherly improved by the Ansager. Then the equation is known as de Broglie-Ansager equation. So what is the mathematical expression for the de Broglie-Ansager equation? So here it is the de Broglie-Ansager equation. So this is known as the de Broglie-Ansager equation. So here lambda v is equal to lambda infinity minus a plus b into lambda infinity into under root c. So here a and b are known as the constants. So c means concentrations in gram equivalent weight, and what are the lambda v? So there is a dilution v. At dilution v, the equivalent conductance. Now here lambda infinity means equivalent conductance at infinity dilution. So here, so in this equation, the solution is diluted. The solution is diluted. The magnitude of the term series, the magnitude of this term decreases, and the equivalent conductance, the lambda v, it is increases. So when the concentration becomes zero, the solution is infinitely diluted, and hence the equivalent conductance, it is appears as a lambda infinity, approaches lambda infinity. So this is known as the de Broglie-Ansager equation.